Hey everyone, I'm Jessica from Aspyre, and today I'll be taking you guys through the final part of our Algebra and Functions unit, logarithmic functions. So what is a logarithmic function? Logarithmic functions are the inverse of exponential functions, meaning all logarithmic functions can be rewritten in exponential form. In the equation x equals a to the power of y is called the logarithm of x. And the equation y equals logarithm base a of x is called a logarithmic function with base a. In the two tables on the right, we have an example of an exponential function and a logarithmic function. The table on the left shows the x and y values of y equals 2 to the power of x, which is an exponential function. The table on the right shows the x and y values within y equals logarithm base 2 of x, which is a logarithmic function with base 2. And these two functions are the inverses of each other. It's important to keep in mind that there are conditions within logarithmic functions. For example, x has to be greater than 0, a also has to be greater than 0, and a can't equal 1. That's because 1 to any power will be equal to 1. Here we have an example of a graph of a logarithmic function where the base is greater than 0 and the base is not equal to 1. On the left, we have an example of what that would look like when the base is greater than 1. It's going to curve upward and then plateau off. And this is an exponential function that is the inverse of this function. And you can see that they are symmetric around the line y equals x. On the graph on the right, we have an example of a logarithmic function where the base is greater than 0 and less than 1. And you can see that the direction is different. It rises in the left direction and plateaus at the bottom instead of at the top. Like exponential functions, logarithmic functions have numerous similar properties to keep in mind. These properties are also very helpful to know when solving problems involving logarithms. First off, let's keep in mind that the base is greater than 0, not equal to 1, m is greater than 0, n is also greater than 0, and t is real. First off, we have the definition of logarithm. Log base a of a is equal to 1, and log base a of 1 is equal to 0. That's because a to the power of 1 is a, and a to the power of 0 is 1. Next, we have the product rule, which states that log base a of m times n is equal to the sum of log base a m and log base a of n. Next, we have the quotient rule, which basically says that log base a of m over n is equal to the difference between log base a of m and log base a of n. Next up, we have the power rule, which states that t, which is a real number, a constant in this case, times log base a of m is equal to log base a of n to the power of t. And the zero exponent rule states that log base a of 1 is equal to 0. The inverse rule states that a to the power of log base a of m is equal to m. And the logarithm with base 10, or log base 10 of m, is called the common logarithmic function, and it is denoted by log m. Now let's try solving a few problems using what we've learned. The first problem asks us to find the value of n if log base 3 of mn is equal to 2, and log base 2 of m is equal to 3. Since we know that log base 3 of mn is equal to 2, by definition of logarithm, we can say that mn is equal to 3 to the power of 2, which is 9. And we also know that log base 2 of m is equal to 3, meaning that m is equal to 2 to the power of 3, or 8. Since mn equals 9 and m equals 8, we can conclude that n is equal to 9 over 8. For a second example, we have two equations. First off, log base 6 of 36 plus log base 6 of y equals 4, and we need to find y. Here we can use the product rule in reverse. So we know that log base 6 of 36 plus log base 6 of y can be combined using the product rule to log base 6 of 36 times y. Then we know that 36y is equal to 6 to the power of 4, meaning y is equal to 36. For second example, we have log base 4 of y is equal to negative 2. We can just use the definition of logarithm to conclude that y is equal to 4 to the power of negative 2, which is equal to 1 over 4 to the power of 2, which equals 1 over 16. Finally, we have the change of base formula. Again, assume that the base is greater than 0, not equal to 1, and b is greater than 0 as well. First, log base a of b is equal to log base m of b over log base m of a, where m is greater than 0 and not equal to 1. Second, log base a of b is also equal to the reciprocal of log base b of a, so we're switching the logarithm and the base to say 1 over log base b of a, and b is not equal to 1. Let's see an example over here at the right. So we're going to try evaluating log base 3 of 30, and we're trying to change the base of log base 30 to log base 10. So looking at this formula over here, we know that log base 3 of 30 equals log base 10 of 30 over log base 10 of 3, which is equal to log 30 over log 3. Thank you for watching our series. We hope this helped. Goodbye and best of luck on all of your future studies. We'll be ready with a new series soon. Thank you.